All right, so we're going to get started with the first of these sessions. So there are 6 main chapters in the book, and so the plan is to go through one every session. Let me make sure that this is recording properly. So we've done this in a while. Okay, it looks good. Sometimes it doesn't start the sound. All right, so we're going to go through chapter 1 today, and chapter 1 is actually just going to be a review of things that are important to know before we start talking about the major topics of this book. So it's not really going to get into photoluminescence stuff today, but it'll sort of set the stage for that in the coming weeks. I think we don't have it next week, but then it'll be back the week after that, if I remember correctly. So a little bit of an irregular schedule, but that'll give you guys time to keep up with the reading if you choose to do that. All right, so the first thing just to go over before we get into things is what are sort of the objectives of this. So what are we going to plan to cover during the 6 weeks or so that we do this? So a big one is going to be mechanisms of photoluminescence, which everybody in my group, we kind of talk about this already at times. So it's going to be, fluorescence versus phosphorescence versus some other related pathways, and how we can use experimental methods to distinguish them. We'll talk about the kinetics of photoluminescent processes, so how we measure and interpret that type of data, what we can do with it, what it tells us about different experimental settings. We will go through a primer on experimental techniques. Obviously, this is best learned in the lab, so those of you that are doing photoluminescence as part of your research, you have to sort of learn on the job because every setup is different and every experiment has its own considerations, but we'll give you some basics on sample preparation, experimental parameters, and how to avoid common mistakes that people make when recording these types of measurements. There'll be one chapter that's sort of descriptive in nature. It's going to cover different classes of photoluminescent compounds. So it'll include things that we're fairly familiar with from our own work, but also some organic molecules, which we don't talk about as much, as well as some materials-based compounds that are luminescent in different ways. So we'll go over how the structure and composition of these different compounds relates to their photoluminescent properties, and then there's a little bit about how to interpret that and how to understand some things about the materials from their photoluminescence. And then the last thing we're going to cover are the applications of photoluminescence, which is going to be different, either chemistry related or things outside of chemistry that require photoluminescence either as an analytical technique or as a key component in a functioning device. And so we'll get into that. One other thing I want to change before I go back is get rid of this thing. Use the PowerPoint pointer. It's a little bit better. Get rid of this. Which one is close? Let's minimize. That's it. Okay. So then let's get on with the next thing. All right, so the first thing we need to review, the stuff that we're going to review today is things that you likely would have covered in either a general chemistry or more advanced undergraduate course. So the book that I wrote is designed to be consumed by either a late undergraduate or early graduate student audience, so someone that has that level of chemistry already sort of in their back pocket. And so these are some of the topics that are going to be important. So the first one that we need to understand, because obviously photoluminescence involves generation of photons by chemical compounds, are the properties of electromagnetic radiation, which is made up of these little packets of energy called photons. So the one that we're going to use the most in sort of characterizing the different photons that are generated is the wavelength lambda. So what you can visualize lambda is, imagine that you have a wave frozen in space. So it's just take a snapshot of a wave right in front of your face, and the distance between equivalent points on the wave is given as lambda. So it's going to be in distance units. So it can either be the peak to peak, as I show here, or it could be the, I guess, what's it called, the inflection point or the 0 point from one point to another, or it can be trough to trough. Any two equivalent points on the wave, as you go through one entire cycle of the wave, that distance is going to be lambda. So you kind of visualize this as a wave frozen in space, and you're just measuring the distance between equivalent points. And you know, as we'll talk about a little bit, lambda can span a very large range of values. So for things like X-rays, lambda is on the order of angstroms or less. For radio waves, it could be on the order of meters, so it spans a wide range of values depending on what type of electromagnetic radiation you're talking about. And then the other property that's closely related to this is the frequency, which is given by the Greek letter nu. And so the way you would want to visualize frequency is, imagine you're watching a wave travel in front of your face, and you can see the intensity oscillation up and down of that electromagnetic wave, and it's the number of times that it oscillates in 1 second. So again, you're watching it going in front of your face, it's oscillating up and down, and the number of times that happens in 1 second is the frequency. So in this diagram here, if we imagine that this axis is a unit of time, where it's showing 1 second, let's say, throughout this whole process, what we can see is in that 1 second, starting here at 0, we go through 1, 2, 3, 4 cycles. So this would be a wave that has a frequency of 4 hertz. Now, obviously, the types of waves that we deal with in photoluminescence in reality are, much higher frequency than this. They're usually in the order of probably megahertz or gigahertz, but nonetheless, that's how we would sort of quantify frequency. And then where this is important is because it determines the sort of classification of the electromagnetic radiation. So there's no real clearly defined difference between the different types of electromagnetic radiation, but they're sort of divided off in terms of different frequency and wavelength ranges. So this is on a wavelength scale that I'm showing here. So anything below 400 is ultraviolet, and you have other classifications even below that. So it'd be gamma rays, X-rays, and then ultraviolet below 400 nanometers, and then 400 to 700. This is the small piece of the electromagnetic spectrum that we can see with our eyes, and so this is the range that is most commonly observed and studied in the context of photoluminescence, especially in applications where you need a visual color readout as part of that process. So we can only see wavelengths from 400 to 700, 400 being sort of violet to blue, and then 700 being the red near infrared borderline. And so right above 700 we call near infrared, and then beyond the infrared region we also have microwaves and radio waves that go to even longer wavelengths. And so that's going to be what we call the electromagnetic spectrum, which is again classified by the different values of wavelength and frequency that we can have, and those two of course are related to each other. Where's that equation? Where'd it go? Oh, there it is. Okay, so the relationship between wavelength and frequency is simple. This is a general chemistry topic that we cover, where you would have the product of those two equaling a constant c, which is the speed of light, which this would be technically the speed of light in a vacuum. It is medium dependent, but in air it's very close to that as well. So that's how those two are related to each other. So higher wavelength, lower frequency, vice versa. And then the other important equation is the energy of a photon, which is given as another constant h times the frequency, or by combining these two equations can be written as h times c divided by lambda. And so h is called Planck's constant, and it has, as you can see, a very small value. So a typical photon has a very tiny amount of energy associated with it, which again is given by the product of that constant with the frequency. But even for the normal frequencies that we would see in visible light, the energy is on the order of 10 to the minus 19 joules for a single photon. So it's a very small amount of energy that we're talking about. So those are going to be how those two are related to each other, and there's really just these two relationships that are important for sort of understanding photons in a more mathematical sense. Now, the other parameter that we often encounter is called spatial frequency, which is abbreviated as nu tilde. That little squiggly line is called a tilde, and it's given as the inverse of the wavelength. And so that's another way that you'll often see, and it's very common, especially in IR spectroscopy. So the x-axis in an IR spectrum is almost always given as a spatial frequency, and we use it sometimes in photoluminescence. Now, the advantage of using this as opposed to just using the wavelength is that this, like the frequency, is directly proportional to photon energy. So sometimes when you're comparing two compounds to one another, or in different contexts, you want to look at, how the energy of the luminescence changes. It's a lot easier to make that comparison if you're reporting it in spatial frequency as opposed to in lambda, which is also very common but is not as useful in some contexts. And it's also just important to be familiar with it because in a lot of the older sort of hardcore spectroscopy literature, spatial frequency was commonly used. Lambda wavelength has become the much more common and conventional way of reporting photoluminescence now. And so obviously, as you guys know, if you use one of the instruments that we have in our lab to record a photoluminescence spectrum, light wavelength is the standard readout. But in a lot of old literature, they use spatial frequency. So these are the common units that we would see. So frequency is always going to be in inverse seconds, which is referred to as hertz, usually modified by some prefix like megahertz or gigahertz, because usually a typical photon that we would study in this context has a pretty large frequency in that unit. The most common wavelength unit is nanometers. As we said, the visible range falls between 400 and 700. That's the unit you'll see most often in context of this research. And then spatial frequency that we just talked about is usually done in inverse centimeters. So it's 1 over the lambda, and then you have to put lambda into centimeters first, and then that inverse is given as what's called the wave number. And then in contexts where you see the energy of a photon reported or the photoluminescence reported in units of energy, which we don't do a lot in molecular chemistry research, but it's fairly common in the materials world. Usually the energy unit that's most common is electron volt eV. And we deal with that sometimes because, for those of us in the group that do photoredox catalysis or things related to that, we often have to convert the emission wavelength or the crossover wavelength in an emission spectrum into an energy unit, and EV is the one that we often use. So you'll see that as well. So those are some relevant things about photons. Now the other topic that's related to this then, which is in a general chemistry course, thinking all the way back to when you guys took that, the thing that's most closely related to photoluminescence and what we're going to be talking about through this whole workshop is atomic absorption and emission. This is probably the first place you encountered some of these ideas. And so this diagram here actually shows the emission processes for hydrogen. Absorption and emission are basically opposite in some sense. Absorption. So when you have an absorption process, you have a photon interacting with a substance. These lines are for hydrogen, as I said, and that causes an electron to go from a lower energy to a higher energy state. So in hydrogen atom, the energy levels are denoted by a single quantum number n, which is an integer value 1, 2, 3, 4, 5, 6, and so on. Absorption of a photon, typically the hydrogen atom would be in the ground state initially, n equals 1, and then it would promote into the higher energy states, n equals 2, 3, 4, 5, 6, and so on. Okay, so that's going to be absorption, where you're going from a small value of n, lower energy, to larger value of n. Now what this diagram is showing are the visible emission lines. So if you have a hydrogen atom or any other atomic substance, any other element, and you excite it to one of these higher energy levels, the electron can also then relax back down to one of the lower energy levels. And in hydrogen, the only visible lines you see, the only ones that occur between 400 and 700 nanometers, are the processes that correspond to terminating at n equals 2. So all the relaxations to the ground state produce ultraviolet UV photons. So it's not that they don't happen, it's just that you can't see them with the visible range. But if you go from n equals 6 to 2, 5 to 2, 4 to 2, or 3 to 2, those are going to give these visible emission lines. Now one thing that this picture sort of shows is that in atomic emission, what you typically have are very narrow lines. So we're showing it as a single wavelength and just a single line spectrum, as it's called, for that type of emission process. As we'll see in molecules, other types of compounds that we work with that are more complex, you typically have broad spectra that cover a range of wavelengths. And we'll get into a little bit about why that is and what that difference occurs from. But this is what atomic absorption and emission looks like. Now we're not going to talk about in detail the sort of theoretical underpinnings of atomic absorption and emission or its applications, which are in many sense very important in other fields. We're going to focus exclusively on different classes of chemical compounds, not elements. But this is what it would look like for an element, and this was probably the first place in your life. I guess I don't know how the general chemistry sequence is in all of your home countries, but at least here in the U.S. we cover this fairly early in general chemistry, and this would be the first place that students typically encounter these concepts of absorption and emission, which we are going to talk about a lot in this course for more complex substances. Now, another thing that's important to realize is once we go and start talking about compounds, we're going to have not just single atomic orbitals that are designated in simple ways by quantum numbers, but we're going to have molecular orbitals that involve, linear combinations of atomic orbitals and, different types of orbitals mixing with each other. And all the photoluminescent processes that can occur are going to involve electrons being, transitioning between different frontier orbitals, filled orbitals, which are occupied in the ground state, and then the empty orbitals they're going to be promoted into upon excitation, and then the luminescence occurs when they fall back down. So we'll get more details about that in the next chapter, but first we want to just cover the different types of frontier orbitals that we're going to need to consider. This diagram here is specific for metal ligand coordination compounds, organometallic compounds, or other types of coordination compounds, which for our own research group, of course, are very important to consider, and we're going to kind of go into some details of that because of its relevance to our own research. So there's different types of frontier orbitals that you need to consider depending on the type of compound you're talking about. So we will talk a little bit about the photoluminescence of organic molecules, and we do that a little bit in our group with the Bodippy, coumarin stuff that we've been working on. And so in those types of molecules, the relevant frontier orbitals, they're shown here, they're abbreviated here as ligand L orbitals, but in reality in an organic molecule they're just, there's no metal, so they would just be the regular pi and pi star orbitals that have. So most organic molecules that are photoluminescent are conjugated, aromatic often, and they're going to have low-lying pi and pi star orbitals that are typically going to be the orbitals that are involved in any sort of photoluminescent process. Now, sometimes non-bonding orbitals, which are lone pairs on heteroatoms, in those can be important as well. So you'll have some combination of those typically being involved for organic molecules. This diagram here, as I said, is relevant to transition metal coordination compounds. And so in coordination compounds, you still have, in many cases, pi and pi star orbitals that can be important as frontier orbitals, especially when your ligands are conjugated, which they are in many photoluminescent compounds. So you'll have those ligand pi and pi star orbitals, which will be perturbed to some extent by coordination to the metal, but more or less they behave as they would in the free ligand. And then you also have your valence d orbitals, which depending on the coordination geometry are going to be split into different energy levels. This diagram here is for the typical octahedral case, where you're going to have 3 lower lying d orbitals that have pi symmetry, and then 2 higher lying d orbitals that are metal ligand sigma antibonding. And so those can be involved as well. And as we'll talk about a little bit later today, different types of transitions are classified depending on which orbitals the electron originates in and which orbitals it terminates in during that transition. And then another class of compounds that we will talk about a little bit are F element compounds. So there are both molecular coordination compounds of the lanthanides and actinides that are luminescent, and then there's a lot of solid state phosphors, so stuff related to like what Bergach's group does in this department, that have F elements as the luminescent center. And so in those types of compounds where the F element is responsible for luminescence, the important orbitals are going to be the valence F orbitals, and sometimes the d orbitals that are a little bit above those. So there's, in F element compounds, there's usually a set of F orbitals, usually 4F if we're talking about the lanthanides, and then right above that is the 5D. Those are really close to each other, so they can both be involved. Now, one thing that's important that we'll talk about later on with F element compounds is that the valence F orbitals do not mix very well with the ligands. So those are going to be minimally perturbed by the ligands. They're going to behave more or less like atomic orbitals, and so that leads to some differences in terms of the appearance of the emission spectra when there's F orbitals involved. And it also, as we'll see, means that the ligand field doesn't really matter as much. You're going to mostly get the same type of emission from those F elements, whether they're in a solid lattice or in a coordination compound. No matter what type of environment they're in, you get pretty much the same emission. So there's some things there that we'll talk about later on. Those are going to be the important valence orbitals for those types of compounds. Now, there's other labeling schemes for frontier orbitals that we should be aware of. So here I'm giving, sort of descriptive labels, L pi, ligand pi, D pi, the D orbitals that mix in a pi fractional label, D sigma star. But there's some other ones that you'll sometimes see. So one that we'll talk about a little bit, and if you've taken my course, which most of you have, at least half of you have anyway, there's about 4 people here that haven't taken my course, I think. But those of you that have, we know we use Mulligan symbols a lot. Those are symmetry-based labels that we can use for any orbital. And you'll see these a lot in sort of some high-level spectroscopy literature, and these are also commonly used for coordination compounds where the relevant electronic transitions involve d orbitals only. It's not as common when you're talking about transitions that involve the ligands, but when you have dd transitions, as we'll talk about a little bit later, you'll see sometimes Mulligan symbols being used as the labels, but it can be used in any context if you're, especially when the symmetry considerations are important. So the Mulligan symbols depend on the point group that you're in, but the most common ones that we would see are, if we're talking about dd transitions, this will be labeled as T2G, this will be labeled as EG. So that's something we went into in a lot of detail in my course, but won't be something we'll talk about a lot in this workshop, but you should be familiar with it. Now, then another class of compounds that we'll talk about are, again, not in great detail because it's not something that I consider myself to be an expert in. It's not something that we do research on in our group, but are going to be luminescent extended solids or nanomaterials, things that have sort of more like semiconductor band structures that give rise to luminescence. So here I have a video that should play, maybe. Did the video not load properly, of course? Why? There it is. All right. So we're going to play a video that shows how this works. So what you have in these compounds, I'll set the stage a little bit. So what you have in these compounds are the orbitals that are filled are called the valence band. In extended solids, you have essentially a continuous band of orbitals. You have so many atoms involved and so much delocalization that the individual orbital levels just stack right on top of each other and more or less appear as a continuous band. So those that are filled in the ground state are called the valence band, and those that are unfilled in the ground state are called the conduction band. Those are going to be empty orbitals that lie above those, and there's going to be some band gap associated with that, which is the energy gap between the valence and the conduction band. And how big this band gap is determines some of the electrical properties. So conductors, things that are metallic, have no band gap. Insulators have large band gaps. And then semiconductors, many of which are luminescent, have sort of intermediate band gaps. So they'll have an energy gap that's sort of on the order of the visible photon range. And then so when you have electrons moving between these, you can get visible absorption or visible emission from that. And there's other things we'll talk about later on with nanomaterials that also control the gap between the valence and conduction band that's important for photoluminescence. So now I have to figure out how to get the play button back. All right, there it is. All right, so let's see what happens when we absorb light. With sufficient energy, we're going to have electrons promoted from the valence band to the conduction band, and then the luminescence would be just the opposite process. So when you do that promotion, you're going to have now holes in the valence band, electrons in the conduction band, and that electron-hole recombination, as is called, the electron falls back down, can give rise to luminescence. So we will talk about that a little bit later on towards the end of this course when we start describing different classes of luminescent compounds. Now, there are other mechanisms for luminescence in extended solids and nanomaterials. They don't necessarily involve these band gap transitions, but that's commonly observed, and that's kind of how it looks. So it's very similar to transitions in molecular compounds. It's just continuous bands of orbitals as opposed to discrete energy levels like we have in molecules. All right, so that's another class I'll talk about. Now, the other thing that we need to define then, in photoluminescence, we're talking about transitions between the excited states and the ground state. Absorption, as we'll talk about, is the opposite, ground state to excited state. And so all those different energy levels in the atom and the molecule and the material are going to be labeled in some way. We call those labels term symbols. Those are symbols that denote different energy levels of a system. Again, this is a topic that we covered a lot in my course if you took it. And so we're going to talk about a few different types of these labels that we'll encounter in the context of photoluminescence. So one that we're going to cover briefly today, but we really won't see it anymore after this, except in the rare cases with F elements, are atomic term symbols. So these are the term symbols that would result from a free atom. So energy levels for a free atom are described in this way, and they're described by a series of quantum numbers symbolized like this here. So they're going to have a spin multiplicity, 2s plus 1. So s is this total spin, which is the 1/2 times the number of unpaired electrons, and then the 2s plus 1 is called the multiplicity. Now, the reason that we report it typically as 2s plus 1 and not just as s is because 2s plus 1 directly gives you the spin degeneracy. And for certain applications, certain contexts, the degeneracy of these states is important. And so we report it, and we'll see this also in molecular term symbols. So it's going to be given as 2s plus 1. The main part of the term symbol is the L value, the total orbital angular momentum quantum number, which is going to be denoted as a letter. So L can have values of 0, 1, 2, 3, 4, 5, and so on. And those are going to be denoted with the letters S, P, D, F, and then alphabetical after that, G, H, skipping J, because J would have sort of ambiguous meaning in this context. So those are the letters that you'll see in the term symbol. Those denote the orbital angular momentum quantum number. We're not going to talk about how to derive term symbols. If you want to review that, go back to my course or talk to me. But anyway, that's what they sort of look like, and they again denote quantum numbers of the system, of the energy level. And then J is sometimes not included, but in the types of F element compounds that we'll discuss a little bit, it is usually part of this. So the J is the total angular momentum quantum number, and this is important when you have a lot of spin-orbit coupling, which we often do for F element compounds. And so this is given as the sum of L plus S. The possible values of J are sum of L plus S down to the absolute value of L minus S, or any number in between spaced by intervals of 1. And so those are going to be the different possible J values you have, and one of those will denote the ground state. Other values of J would then denote excited states above that. All right. So when this is relevant is going to be if you're talking about atomic spectroscopy, which we're not going to really cover in this, but as I said, we use these atomic term symbol labels very commonly for F element complexes because, as we said, in those compounds, the F orbitals don't mix very well with the ligand, so they more or less behave like atomic orbitals, and then we still use the atomic orbital sort of convention for labeling their energy levels. All right, so that's where we're going to see that. Now, another one that we will see are going to be symmetry-based term symbols that we'll often encounter in molecular compounds. And so this would be given as, again, spin multiplicity is still included, 2s plus 1. And then you're going to have a Mulligan symbol that denotes the symmetry of that energy level, the symmetry of that term. And so that depends, which Mulligan symbols you have depend on the point group. And most of the photoluminescent compounds that we will discuss in this course are going to be closed shell molecules. So those are going to be molecules that have S equals 0 in the ground state. All of the electrons are paired. All the orbitals are either doubly filled or completely empty, however you want to think about it. And so in closed shell molecules, things that have a singlet ground state and have totally closed shell electron configuration, the ground state term symbol is always the totally symmetric representation for that point group. So as an example, if we have the simple organic molecule benzene, the point group is D6H. Benzene, as we know, is a closed shell molecule, is diamagnetic. All the electrons are paired. And so the ground state term symbol for benzene would be singlet A1G. So that's the totally symmetric representation in the D6H point group. Now, if you want to figure out what the excited state term symbols are, you need to consider the orbitals that are involved. So in an excited state, which is an energy level above the ground state, you're going to take one or more electrons and promote them from a filled orbital to an empty orbital. You're going to promote them to a higher energy level. So the most common one that we talk about for molecules is going to be the HOMO to LUMO transition, where we take one electron from the HOMO and promote it to the LUMO. And the way that you get the term symbols for those excited states is going to be by taking the direct product of the two orbitals that are involved. And this is only true for closed shell molecules generally. For open shell molecules, getting the excited state term symbols is more complicated. But for closed shell molecules, where you're just promoting a single electron from a doubly filled orbital into an empty orbital, in that case, you can have either singlet or triplet. Let me sketch this out real quick. Let me write. We have to change the pen, I think. So again, in those situations, I don't have a diagram, but this could be helpful. You have your HOMO and your LUMO. I hate writing in PowerPoint, it's terrible. All right, so you have your HOMO and your LUMO. Initially, your HOMO is doubly filled, your LUMO is empty. That's the ground state, and then the excited state, we take one electron and we promote it. And once the two electrons are in two different energy levels, they can be either the same spin or opposite spins. So this is showing the situation where their spin is opposite, which would be a singlet state, still S equals 0. But because they're no longer in the same energy level, the electrons can also be aligned. They can have the same spin, which would be a triplet state. So you get the symmetry of that by taking the direct product of the two orbitals. So for benzene, as we said, the HOMO is E1G and the LUMO is E2U. The direct product of those two gives you the symmetry of the term, and then that can be singlet or triplet. So that one electron transition actually gives you a bunch of possible term symbols that are shown here. But that's those are the types of labels that we will see when symmetry-based considerations are important. And as I said earlier, for DD transitions, which aren't very commonly involved in luminescence, but if you were looking at that type of context, those are the term symbols. You'll see those Mulligan symbols. All right, and then the one that's I guess that's duplicate information. Sorry, I should have shown this diagram before. I forgot that I changed this. I didn't change it completely. So this is the orbital diagram for benzene. Joao can tell me if this is wrong or not, because this group knows all about aromaticity, right? So this is what the frontier orbitals of benzene look like, the pi orbitals in particular, which are involved. And as we said, the HOMO is E1G, LUMO is E2U, and those are the different term symbols together we just went through. So I messed that up a little bit, but that's a diagram that can help put that in a little bit more detail. Another convention that we use for labeling different energy levels, which we use it a lot in our own research, and it's common in both organic and organometallic photochemistry, is this convention using S and T labels. So this is relevant for closed shell molecules, which, as I said, most luminescent compounds, especially coordination compounds, are closed shell, and which means they're going to have singlet ground states, S equals 0 to S plus 1 equals 1. And then, as we talked about in the context of benzene, the only possible excited states when you have a singlet ground state for single electron transitions is going to be either a singlet excited state, also S equals 0, or a triplet excited state when the two electrons are aligned and you get S equals 1. So those are the only two possibilities. So then we just label all the different energy levels as either S for singlet, T for triplet, and numerical subscripts just tell us what order they come in. So by convention, the ground state always has a subscript of 0. So in that case, in almost every case, the ground state would be S0, a singlet state, and that's the lowest one. We only use 0 for the ground state. We don't use 0 for any excited states. In rare cases, you'd have a triplet ground state, so it would be T0, but again, in all the ones we'll talk about, it's going to be S0 for the ground state. And then excited states have numerical subscripts greater than 0, integer subscripts 1, 2, 3, and so on, that indicate the relative energy ordering within that spin multiplicity. So S1, S2, and S3 would all be singlet excited states, and that would be the order that they would come in. S1 is the lowest energy singlet, then S2, and then S3. And then within the triplet excited states, you have T1, T2, T3, and so on. And again, if you have a singlet ground state, you would not have a T0 state, because 0 is only used for the ground state. And again, we can't tell the relative ordering of the singlets and triplets from this nomenclature. So in almost every case, T1 is lower than S1, but we can't tell easily is T2 also lower than S1 or not. You can't really easily compare the singlet and triplet states to each other, but within each spin manifold, within each spin multiplicity, the ordering of the states is given directly by those subscripts. In most cases, as we will also talk about next time a little bit, S1 and T1 are going to be the most important excited states. And so there's going to be these higher order states that can be populated upon excitation in many cases, but luminescent processes almost always occur from S1 or T1, not from the higher energy states. So now we've been talking a lot about different ways of labeling the ground state and the excited state. I can tell you one of my favorite jokes, which I tell to my general chemistry students, but probably haven't said to you guys. So which one is going to be lower in energy, a hamburger or a steak?
Hamburger.
Why?
So steak's too high.
Almost. You're right on hamburger, but the reasoning's a little bit off.
Okay. Ground beef.
Yes, you're on the right track. So it's going to be
I don't know
because it's in a ground state. Yes. So hamburger has lower energy because it's in a ground state. All right. So now you guys know my favorite joke. Maybe you'll always remember that what a ground state is then. All right. So that's another convention that we will see, and then finally the last one, which comes back to this diagram that I showed earlier, are descriptive abbreviations that tell you sort of the nature of the electronic transition that gives rise to that excited state. This is, again, very common in coordination compounds or organometallic compounds that we work with. And so you can have different types based on the different possible transitions between frontier orbitals. So one type, which is shown in blue here, would be if you have a ligand-centered transition, basically involving electrons going from the filled pi orbitals on the ligand to the empty pi star, or this same type of label, pi to pi star, would be used for simple organic molecules that don't have d orbitals involved, but you have that type of transition being very, very prominent. So those are labeled as pi to pi star, or in a coordination compound as ligand-centered, or IL for intraligand. So that tells you the types of orbitals that are involved in the transition, and those will be ones that involve exclusively the ligand or any other sort of organic functionality in the molecule. Another type, which we will talk about just in one class of compounds later on, are these DD or metal-centered transitions. So those involve transitions, these would only be occurring in compounds that have between 1 and 9 d electrons, so they have to have empty d orbitals and filled d orbitals. So they'll have a transition from a filled to an empty d orbital, and those are labeled as DD transitions, metal-centered transitions, or sometimes ligand field transitions is another term that you'll see for those, and that's going to be shown in red here in this diagram. In green and magenta, we have the two types of charge transfer transitions. So charge transfer involves an electron being promoted from an orbital that's primarily centered on one part of the molecule into an orbital that's primarily centered on a different part of the molecule. That's why we call it charge transfer. So the two types that occur in metal-ligand coordination compounds are ligand to metal charge transfer. So that's going to be a transition from a filled pi orbital into an empty d orbital. It could be the d pi or the d sigma in reality, but it's going to be that type of transition where in the ground state the orbital is mostly localized on the ligand, usually a pi or sometimes sigma in rare cases, and then in the excited state that promotes into an empty d orbital. So that's called ligand to metal charge transfer, and it's not as common in photoluminescent compounds, although there is a lot of emerging research using LMCT excited states for photosensitizers, and many of those are luminescent, so it is coming on, but not nearly as common as some of the other ones. An example of LMCT would be, I don't know if has anybody here seen what like potassium permanganate looks like? It's like a bright pink or purple compound, and when you dissolve it in solution, it has that sort of nice magenta. That's an LMCT transition. So you have filled orbitals on oxygen. The metal is D0, so there's no d electrons, and so the transition goes from those oxygen-centered orbitals into the empty d orbitals, and that's called LMCT. And then the one that's very common in photochemistry and has been developed historically since at least the 1950s is metal to ligand charge transfer, MLCT. So this occurs a lot in coordination compounds that have relatively high numbers of d electrons. So we're talking about like D6 through D10 is where you see this the most. And that's going to be a transition from a filled d orbital. It could be the d pi or the d sigma star if it's occupied, but it terminates at an empty ligand pi star orbital. So that's metal to ligand charge transfer, the type that we see all the time in the types of compounds that we work with. So those are the other types of abbreviations that we'll see where it sort of tells you the nature of the excited state. So it's a little bit more informative than just using the Mulligan symbol, which only gives you the symmetry, or the S1, T1 type of labels, which only give you the multiplicity. This gives you some more information about the type of excited state, so it's commonly encountered as well. And often you will append the spin multiplicity onto these. So a ligand center state would be, that's a singlet, would be singlet LC, for example, or triplet MLC would be a triple state that's metal ligand charge transfer, and so on. So spin multiplicities are often included. Again, these are most relevant for closed shell compounds, so you're going to usually see singlets or triplets being involved. All right, now another thing that's important to appreciate about the energy levels in any type of compound really is going to be the superposition of vibrational energy levels within each electronic energy level. So in reality, the electronic states are not just represented as a sort of single horizontal energy level. They're represented as potential wells. In reality, they're three-dimensional wells, as I'm sure Joe Al could tell you, is something I think about a lot in computational research, but they're best represented pictorially as these sort of two-dimensional wells. And so essentially what you have for these potential energy wells or potential energy surfaces, they're sometimes called, is the horizontal axis is going to be the distortion of the molecule along some axis or along some direction of motion, and then that's going to be how the energy of that state changes. And so they all have these sort of, wells associated with them. In the harmonic approximation, that's basically the approximation that chemical bonds act like perfect springs, that you can stretch them as far as you want. You would get these parabolic wells, and you would get vibrational energy levels that are spaced equally within that. Now, in reality, you can't stretch molecules as far as you want. Eventually, you're going to break the bonds, and so the real situation is anharmonic wells, whereas you stretch the molecule to too much of an extreme, you dissociate, so your potential energy surface flattens out as you go to the extreme of basically pulling the molecule apart. The atoms are no longer bound in that state. And the result of that on the vibrational energy levels is that they tend to get closer and closer together as you go to higher and higher vibrational states. Although in reality, for photoluminescence, where we're going to mostly concern ourselves with these first few vibrational energy levels, and they're still pretty evenly spaced. They're going to be a little bit compressed as you go up, but it's not going to be obvious until you get really high in energy. All right, so we'll talk about later on why those energy levels, vibrational states, are also important in photoluminescent mode, in photoluminescent transitions. But some important things to know, in any molecule, you're going to have 3n-6 normal modes, and then each of those normal modes is going to have a fundamental frequency associated with it. So the spacing of these energy levels is approximately given by h times that fundamental frequency. And again, it's more complicated than that for the anharmonic wells, but that's a rough estimate of how far apart those energy levels are. And it's also important to realize that they're about one order of magnitude smaller than the energy differences between the electronic states. So in a typical, visible transition, you're going to have electronic energy levels that are on the order of 10,000 or more wave numbers. If you're talking about the visible range, it's going to be roughly that's like 25,000 to about 12,000 wave numbers is the visible range, 400 to 800. And so your electronic transitions are going to occur on that order, tens of thousands of wave numbers. And the vibrational energy levels that are superimposed on those are going to be on the order of just a few thousand at the most. So it's about an order of magnitude smaller. So those can change the appearance of the spectrum, and in IR spectroscopy we study those transitions separately, but in the types of electronic spectroscopies that we're talking about, photoluminescence in particular, the existence of these vibrational energy levels can change the profile of the emission. They can have some important consequences on that as well, which we'll talk about. And there's a lot of different types of vibrational modes, but those that are most often associated with either absorption or emission transitions are what are called totally symmetric modes. So example, in an octahedral compound, that would be what you call your breathing mode, where basically all of the ligands are stretching in the same direction, and is a totally symmetric stretch. Those are most important in photoluminescence because those don't really change the symmetry basis of the electronic transition. So in order for the electronic transition to occur, as we'll talk about a little bit today, it has to follow some symmetry-based selection rules. And if you couple that with a totally symmetric mode, that doesn't alter the symmetry basis, because anytime you just multiply something by a totally symmetric mode, the symmetry doesn't change in that direct product. And so those totally symmetric modes can couple with those electronic transitions without perturbing the symmetry-based selection rules that are involved in that transition in the first place. So you'll usually see totally symmetric modes that couple, but that's not always the case. All right, another technique that we'll talk about today that's related to photoluminescence and is often, one of the first things you study as part of a interrogation of a photoluminescent compound is UVVis absorption. Now, we talked about it in the context of atomic absorption and emission. They're more or less opposite processes. So in an absorption experiment, you're irradiating, what's going on here? What did you guys do? In an absorption experiment, it's more or less the opposite of emission. So you're starting with the sample in the ground state, you're irradiating it with photons, and if the photon has the appropriate energy to promote it to an excited state, you're going to cause that substance to go to that higher energy state, and you're going to measure then the wavelengths at which that occurs. So this is first just a diagram of the typical experiment. So you have incident irradiation that goes into the sample. Simply do it one wavelength or one frequency at a time. And then as that light passes through the sample, it's going to go in with certain intensity I0. And then as it passes through, the intensity is going to be attenuated by some amount, which is given as I here. And so the typical readout for a UVVis absorption experiment is what's called absorbance, which is the negative log of that intensity ratio, I over I0, or the negative log of the transmittance T. All right? And sometimes in IR, you actually use transmittance directly instead of absorbance, but they're related to each other. And then the relationship that's very important for absorption spectroscopy as well is called the Lambert-Beer law, or more simply the Beer's law, which is that the absorbance is linearly proportional to three things. And so I'll define these here. So A is absorbance. That's the quantity we most often record and report. And as we defined earlier, that's the intensity, and the transmittance is the ratio of those two. But those three terms, epsilon, C, and the path length, we're all familiar with from our research. Epsilon is the molar absorptivity, or what's called the extinction coefficient. And for those in the computational world, that's directly related to the oscillator strength of the transition. So that's essentially a reading of how intense the transition is. It's a good way to sort of give an apples-to-apples comparison between different substances. Because if you just read absorbance, that's also dependent on the concentration and the path length. And that's what those other two terms are. So C is the molar concentration of the sample, and then L is the path length, which is, again, diagrammed here as the length of the sample, usually 1 centimeter for a typical absorption experiment. All right, now there's also theoretical considerations for UVVis absorption. So, when does the transition occur? How do we decide how intense it is? What determines the value of epsilon, or the value of the oscillator strength for that transition? So the first thing is, again, sort of the energetic consideration that we already talked about. If you absorb a photon with sufficient energy to promote the electron from the ground state to the excited state, that can happen. And then there's going to be two main selection rules that determine the probability of that transition. In other words, how likely is that transition to occur? Well, that would result then in higher molar absorptivity or higher oscillator strength if there's a higher transition probability. So this is all sort of comes from quantum mechanics, but there's a symmetry basis to it. But the easy part of it is the spin selection rule. So only transitions to excited states with the same spin as the ground state are allowed. So that means in the typical case that we have a singlet ground state S0 for most of the compounds we'll talk about, only the UVVis transitions that result in population of these singlet excited states, S1, S2, S3, and so on, will be spin allowed. All right, so as an example, if we have an S0 to S1 transition, that would be spin allowed. S0 to T1 would be spin forbidden, which means that the molar absorptivity or oscillator strength would be basically 0. Now, for some of the compounds we work with iridium and perhaps platinum as well, you can sometimes see direct singlet to triplet transitions in the UVVis. They're usually very weak. They'd be those lower energy transitions, often have epsilon values that are on the order of a few hundred at the most, but we can sometimes see them. But those are very weak compared to the spin-allowed singlet transitions. Now there's also an electric dipole selection. This is not very important for photoluminescence research, but again, something we did cover in my course, and it has a little bit of importance in some cases for photoluminescence, which is that a transition is electric dipole allowed if the direct product of the ground state and the excited state transform as one or more of the Cartesian coordinates. Now, there are other selection rules that can sometimes be important for other classes of compounds, but electric dipole transitions are going to be the ones that dominate molecular compounds in particular that we work with in our group. So if we go back to benzene example that we gave earlier, we said that the ground state term symbol is totally symmetric, singlet A1G. And if we do the transition from the HOMO to LUMO, that generated the following excited states, which was given to just the direct product of the two orbitals. And by analyzing the selection rules, what we can do is to find out if the transition is allowed. For the electric dipole selection rule, we have to take the direct product of the ground state, which is A1G, with all the different excited states. But since the ground state is totally symmetric, that doesn't really change. The product is just the same symmetry as the excited state itself, so that's sort of a trivial operation. And so we get these direct products, B1U, B2U, and E1U. And then if we look at a D6H character table, we would find that E1U transforms as two of the three Cartesian coordinates, X and Y. And so that means the transition into the E1U terms are going to be electric dipole allowed. And so that means this transition, the singlet A1G ground state to the singlet E1U, is spin allowed because it's a singlet to singlet transition, and it's electric dipole allowed because it goes to an excited state E1U that transforms as the X and Y coordinates. So those are the symmetry-based selection rules that can also be important for determining how intense a transition would be. All right, I think this is the last major topic we'll cover today is kinetics. So we will talk about, as I said, one of the major learning outcomes, learning objectives for this course is going to be the kinetics of photoluminescent transitions, how we measure that, how we can use that to understand some things about the compound and about the process that's occurring. And so we have to consider simple rate laws for different types of kinetic processes. Now, fortunately for us, for most photoluminescence things that you're going to look at, it's pretty simple rate laws, pretty simple kinetics involved. It's going to be usually first order. Because it's, in most cases, what we're going to be analyzing is just an excited state molecule decaying to the ground state. So it's a unimolecular transition. And so generally speaking, unimolecular transition means just a single species decaying to something else. In the context of photoluminescence, that's an excited state going to a ground state. And so for that, the kinetics are very simple. The derivative, the change of the concentration of A as a function of time is just equal to negative of a rate constant K multiplied by the concentration of that species. That's the first order decay rate law. Now the integrated rate law then, which is often more useful, is going to be just taking the integral of this, and so you would get then this relationship here. The concentration of A, whatever the decaying species is going to be given as the initial concentration, A0, multiplied by this exponential term, e to the minus kt, where again K is a first order rate constant. Or the way that we often rewrite it and analyze it in the context of photoluminescence is taking 1 over K and calling it tau, the time constant, or the lifetime as we often term it. So those are two different ways of writing the same integrated rate law in terms of either K or in terms of tau. All right, now sometimes we will encounter second order kinetics. So we are going to talk a little bit about excited state quenching, which is where we generate an excited state and then it reacts with something else before luminescence can occur, or in competition with luminescence, as is often the case. And so in that case, you have to consider sometimes second order processes where two species react with each other in a bimolecular fashion. So the rate law for this is relatively simple in terms of its derivative form. The change in concentration of A as a function of time is the rate constant times the product of the two, A times B, or the change in P as a function of time is equal to just the positive, that the net, K times A times B. So it's a product of both concentrations in this case. But the integrated rate law for this is fairly complicated because it depends on both A and B. It depends on the initial concentrations of both A and B. And so it's a very complicated rate law to try to consider. So I'm not going to show it mathematically, but normally what we would do, especially in photoluminescence research, is we use what are called pseudo first order conditions. And so the way that works is that we have a bimolecular reaction, which is going to have a rate law that's dependent on both concentrations, but we'll set it up so that one of the concentrations is much larger than the other. And so for those of you in our group that do quenching experiments, that's typically how it is. The concentration of the quencher is going to be much higher than the concentration of whatever excited state is reacting with. And so in that situation, if the concentration of one thing, which I'm calling B here, if the initial concentration is much larger than the concentration of A, that means that the concentration of B more or less remains constant during the whole process. So then what we can do is we can treat this as a first order reaction where this observed rate constant is actually the product of the inherent second order rate constant and the concentration of B, which is unchanged during the reaction. So your integrated rate law would look very similar. The only difference now is that the observed rate constant is a function of the concentration of whatever you're reacting with. So if you change the initial concentration of B, you will change the observed rate constant. That's how we do those types of quenching experiments. But that's what's called pseudo first order conditions, where you can more or less set this up as a first order decay of species A, but just the rate constant depends on that concentration of B that's present, which is more or less constant during the reaction. So those are how second order kinetics work. Now another thing that we encounter a lot in photoluminescence, and really it almost happens every time that we're analyzing this, is where we would have parallel pathways occurring. So you have a single species A, which again in our case is going to be an excited state, but that excited state can decay or react via two or more different pathways simultaneously. So it can either have a decay to two different things, this is not very common in photoluminescence, or it can have two different pathways that get you to the same final state. So this would be, in our case, as we'll talk about in the next chapter, if you have an excited state that you form, it's going to undergo radiative decay would be one pathway, non-radiative decay would be the other. They both get you to the ground state, but there are two different pathways that get you there. So these are two different possible processes that involve the same species undergoing parallel reactions. But in either case, the kinetics work out the same. It doesn't matter which of these is actually occurring. But the decay of A is going to be the sum of two first order processes now, where they each have their own associated rate constant K1 and K2. And then you can just group those rate constants together as K1 plus K2. And so then what that means is that your first order integrated rate law is going to be a function of two rate constants, which can be summed together as your observed rate constant K, or your observed lifetime is going to now be a function of both rate constants K1 and K2. And then the other thing that I'm not going to be showing here explicitly is that sometimes one of these processes can be second order. So you can have an observed rate constant that's a sum of a first order and second order process as well. But again, if it's pseudo first order, it would just be a rate constant times an initial concentration. So you'll sometimes see that in quenching pathways. I don't go through that, do I? No. So that's, again, in these expressions here, the observed rate constant is the sum of the two, or if you're doing it in terms of lifetime, it's going to be the inverse of that sum, 1 over K1 plus K2. Or if one of these was a second order process, I guess I can sketch that out real quickly. So if you had this is what essentially happens in quenching. So you would have so if one of those is second order, so it's A is undergoing a first order process to form something else, and a simultaneous second order process. In that case, the decay of A is going to be the first order process plus the second order process, where the second order process is given as a product of, and if it's pseudo first order, again, it can just be thought of as the initial concentration of B, which is constant during that process if the concentration of B is much larger. And so then your integrated rate law would be written like that, and your observed rate constant would be the sum of the first order rate constant and the second order process, which is a function of the concentration of B if it's in a pseudo first order situation. So that would be just a slight extension that involves the second order process. So this is what we would see in any quenching experiment that we'll talk about later. And actually in the quenching experiments you really have three processes. You have two first order processes, non-radiative, radiative, and a second order process, where that's going to involve the quencher. So this will start to make more sense in how we, why we actually needed to think about this stuff when we start talking about kinetics and quenching. That's going to come later on. But you should, at the very least, be familiar with how to write and understand simple rate laws for both first order and second order processes, because both of those can be encountered in photoluminescence research. All right, I think that's the last slide. Yep. So any questions on what we covered today? All right, so I won't belabor the point. I'll stop there. And as I said, we'll be back in a couple of weeks with the next one, where we'll actually start talking about photoluminescence. So in the meantime, I'll have this video posted somewhere and put the link in the Slack page. So if you want to review it, or if anybody that's not here wants to watch it,